Now we turn to merge sort. It takes a very different path. It splits the array, sorts each half, and then merges the sorted halves back together. Now let's meet merge sort. It has 3 simple moves. Split the array in half, sort each half on its own, then merge the 2 sorted halves back into one. Think of 2 piles of graded exams. Each pile is already sorted by score. To make one combined sorted pile, you look at the top paper of each pile, take the lower one and repeat. Each step is one small comparison. The base case is tiny. An array of 0 or 1 element is already sorted, so there is nothing to do. The recursive case does the splitting. We sort the left half, then sort the right half, each the same way. Then we combine. We merge the 2 sorted halves into one longer sorted run. The key idea is simple. All the real comparing happens in the merge step. The recursion only decides which 2 sorted runs to merge next. This picture shows the whole recursion as a tree. The full array sits at the top. Each step below it splits an array into 2 halves. The top array splits into a left half and a right half. Each half splits again and again until every piece holds just 1 element. The green boxes at the bottom are the base cases, size 1 or less. Because we always cut exactly in half, the tree is log base 2 of n levels deep. Then the merges climb back up. Here is the property that makes merge sort predictable. This tree shape never degrades. Merge sort always splits exactly in half, so its recursion depth is always log base 2 of n, no matter what order the input arrives in. Quicksort's tree, coming next, has no such guarantee. Let's read the pseudocode. Merge sort is the recursion. If low is less than high, there is more than 1 element, so we find the midpoint. Mid is low plus high minus low over 2. Then we sort the left half, sort the right half, and merge the 2 sorted halves. Now look at merge. It uses 3 cursors. I starts at low and walks the left half. J starts at mid plus 1 and walks the right half. K writes into the aux array. While both halves still have elements, we compare their 2 heads. If A at index I is less than or equal to at index J, we copy from the left. Otherwise, we copy from the right. Using less than or equal, not less than, keeps equal keys in their original order, so the sort stays stable. At the end, we copy any leftovers, then copy aux back into A. This is the merge step. We have 2 sorted piles and an empty helper array called aux. The head of each pile is its smallest value left. The left head is 3 and the right head is 9. We compare the 2 heads. Copy 1. 3 is less than or equal to 9, so 3 wins. It turns green and drops into aux at index 0. Its source cell goes dim. The value is consumed, but it stays there, not deleted. The new left head is 27. Copy 2. The heads are 27 and 9. 9 is smaller, so 9 wins and drops into aux at index 1. Its right cell goes dim. The new right head is 10. Copy 3. The heads are 27 and 10. 10 is smaller, so 10 drops into aux at index 2. The new right head is 82. Copy 4. The heads are 27 and 82. Now 27 is smaller, so it drops into aux at index 3. The new left head is 38. Copy 5. The heads are 38 and 82. 38 is smaller, so it drops into aux at index 4. The new left head is 43. Copy 6. The heads are 43 and 82. 43 is smaller, so it drops into aux at index 5. Now the left pile is empty. Copy 7. The left pile is empty, so there is nothing to compare. We just drain the last right value 82 into aux at index 6. Aux is now one sorted run, all green. We copy aux back into A, slot for slot. 7 values took 7 copies, so each value is copied once. Because a tie takes from the left pile first, merge sort is stable. A quick check on that merge. Which run's head was copied into the auxiliary array first, the 3 or the 9, and why? Pause and answer. The answer is 3, the left run's head. The very first comparison is 3 against 9, and 3 is smaller, so it goes first. A second check, this one about the invariant. Is merge sort stable, and why does that matter? Pause and think. The answer is yes. The merge step's tie rule takes from the left run on equal keys, using less than or equal. So an element that started earlier never gets placed after an equal element that started later. And here is why it matters. Whenever records are sorted by one field, and a second field's original order should survive. For example, sorting log entries by severity while keeping same severity entries in timestamp order. This is merge sort in C. The merge function takes the array a scratch array called aux, and the 3 indices low, mid, and high. We set I to low, j to mid plus 1, and k to low. I walks the left half, j walks the right half, and k writes into aux. While both still have elements, we keep merging. We compare the two heads. If A at index I is less than or equal to that index j, we copy at I into aux. Otherwise, we copy A at j using less than or equal. Not less than keeps equal keys stable. When one half runs out, the other may still have values. If the left half has leftovers, we copy them straight into aux. And if the right half has leftovers, we copy those too. Then mempy copies the merged run from aux back into A, so it now holds the sorted result. The merge sort function is the one you call. It takes the array and its size n. If n is less than 2, the array is already sorted, so we return right away. We allocate the aux array once, big enough for the whole array. The recursive helper then sorts the whole range, from 0 to n-1. When it finishes, we free aux. This function owns aux, so it frees what it owns. Merge sort's cost is the same in every case. Best, average, and worst are all big O of n log, and the balanced tree guarantees it every time. It is stable, and it is not in place. It needs big O of n extra space for the auxiliary array. Now the trade. You may think merge sort simply beats quicksort because it has no big O of n squared worst case. But it pays big O of n extra memory that quicksort never needs. And on large in-memory arrays, that second array is exactly why quicksort is often preferred anyway, despite its worst case. The full program allocates the auxiliary array once per call, and frees it before returning.